Okay, no more residues, at least for a while. We're going to now talk about Moebius transforms, which are named after the German mathematician Moebius, whose main contribution to mathematics was to invent Moebius transforms. And that is what counts for humor in an advanced math class. Let's take a look at what Moebius transforms do. The main idea is that we want to track what a function does to a region. So basically, given a region R, we want to determine the shape and position of the region f of R, where f is an analytic function. That is a very good visual exercise. It allows you to really determine how a shape is being deformed by a transformation. It trains the ability, therefore, to visualize flows, for example, for fluids. It reveals the geometric aspect of functions that is not really present for functions on the real line, and that's because the real line is one-dimensional. You take an interval, you stick it into a differentiable function, you get an interval back, and that's it. Here, with this second dimension, this extra dimension of the complex numbers, we can do a little bit more on the geometric side. In this first presentation, and we're going to talk about these deformations a little bit longer than just one transformation, we will ultimately investigate the so-called Moebius transforms, and yeah, they really are named after a gentleman named Moebius, and I would presume that he was the one who, for the first time, really investigated these transforms. They're also called fractional linear transforms, and basically they are of the form f of z equals az plus b over cz plus d. And you can rightly say that, well, those functions actually are already quite complicated, and indeed it would be, at least for me, not possible to really track the cumulative geometric effect of a transformation like that just from that formula. But here is where we're also going to very much train our ability to break a function up into a composition of simpler functions, because take a look at this. Like I say, as such, they seem hard to analyze, but this function, f of z equals az plus b over cz plus d, can be represented as a composition of simpler functions. So I could take my z and I could map it to cz, and that would be just applying the function f of z equals number times z, and you can see up here in our table of contents that we will investigate various simpler functions separately. So yeah, I could go from z to cz, from z to cz, by just multiplying by a number. I can go from there to cz plus d by just adding a number. I can go from there to 1 over cz plus d by taking this result and plugging it into the function 1 over z, into the function that multiplies everything to its reciprocal. I can go from there to this expression, and even though this looks complicated, I'm just multiplying with a number. So this is another application of this function here. And I can go from there to this expression. Well, all I've done here is I've taken this term out front, put it in the numerator, and then added another term, so I've only applied this function one more time. And then we do a little bit of algebra with that. We find the common denominator, and as we find the common denominator, well, a over c times cz is az, and a over c times d is dA over c, and you can see now that the dA over c's cancel, and we actually end up with az plus b over cz plus d. Especially in this part of the course, this approach of taking a function and breaking it down into a composition of functions that we have a chance to analyze is very, very common, and so as we go through this, you will develop quite an eye for these kinds of decompositions. Okay, so what that means for the task at hand, for the first task at hand, which is ultimately to analyze Moebius transforms, is we must investigate what the functions f of z equals z plus b, f of z equals az, and f of z equals 1 over z, what these functions do to an input region. And we will here pay special attention to what these functions do to circles and straight lines, and that is because ultimately it turns out that Moebius transforms map circles and straight lines to circles and straight lines. They might map circles to lines, some circles to lines, and some lines to circles, but overall the union of these geometric objects will be mapped to itself. And if we're thinking of the complex plane, then that does make a bit of sense, because a straight line could always be interpreted as a circle with infinite radius. That feels a little strange, but it is actually something that is quite sensible to do here. Okay, so let's take a look at the function f of z equals z plus b. Well, that function takes a region and shifts it by b, right? That's all it does. So if we have a point b, a point is of course always to be identified with its position vector. And if we then have a region r here, well, then all we do is we attach this position vector and shift the whole region by that vector to get the image region there. In particular, that means that circles are mapped to circles and lines are mapped by lines, because those things are what is called translation invariant under a straight translation by a vector b or by a point b. Okay, the function f of z equals az is a little bit more complicated. Let's just say that a is equal to s times e to the I theta. That maps the region R to a region obtained from R by stretching it by the factor S, right? That's why I call this thing S. It's a stretch factor. And then rotating it by an angle theta around the origin, because multiplying by e to the I theta, we know that that is a rotation. Okay, I'm not going to give a picture with a region, but I can do this with a point, right? Here's a point Z. I just put a line through that. And first of all, as I push this thing out, the point Z becomes the point SZ. So that's where the stretch factor, depending on how big or how small z is, the stretch factor is either huge or not so huge, but either way, the stretch factor only pushes the point z radially farther out, or if the stretch factor is smaller than 1, pulls it in. And then we also have this angle theta, and that just rotates the result by that angle theta, and so s e to the I theta z is over here, and that's a times z. Again, in particular, if you take a circle and stretch it, you get another circle. And if you take a line and stretch it, you get another line. And similar for rotation. So this thing maps circles to circles and lines to lines. As an example, and here's where we want to start practicing these visualizations, let's find the image of the square -1, 1 cross -1, 1 under the function f of z equals 1 minus I times z plus 1 plus I. Okay, so we're mixing the real notation, where we're interpreting the plane as R2, with the complex notation. That is something that can also become fairly common here. Shouldn't bother us too much though. So first of all, the square is mapped to the square -1, 1 cross -1, 1 plus 1 plus I. Well, if you add 1 plus I to it, that means you're shifting 1 to the right and 1 up, which means you're taking the square -1, 1 cross -1, 1, and you map it to 0, 2 cross 0, 2. If you then multiply by 1 minus I, and 1 minus I in polar notation is square root of 2 e to the negative I pi over 4, first stretches it by a factor √2, which produces, of course, the square 0, 2 times √2 cross 0, 2 times √2 as an intermediate result. And then the multiplication also rotates this intermediate square by negative pi over 4, so it rotates by pi over 4 in the negative mathematically negative direction, in the clockwise direction. Okay, so you can also see here, just as we had in the more abstract introduction, the way to figure this out is to take your function and break it up into pieces where you can see what's going on. And so the result here, of course, then is, well, here we go. Here's the original square, -1, 1 cross -1, 1. We push over and push up to get 0, 2, 0, 2. Then we stretch, we get 0, 2 times √2, 0, 2 times √2. And then we do the rotation by pi over 4. And so that's the picture. I didn't encode this one as a set, because that is rather hard to do. And I think the homework problem from which this particular example was inspired actually just wanted to have a picture. And if that is the case, then sometimes just drawing a series of pictures like that really is as good as anything else. This is supposed to train visualization in conjunction with the algebra, of course. Okay, so we could also note here that f of z equals 1 minus I z times z plus 1 plus I, that's the same as 1 minus I times z plus, well, and 1 minus I times 1 plus I, that's 2, right? And so that would mean the multiplication by 1 minus I is a stretch by root 2 and a rotation by negative pi over 4. So it would first stretch the square that is still centered at the origin and then rotate it into a diamond shape. And then, well, yeah, that would be the diamond shape. And adding 2 puts the shape in the right position for us. So there are several ways to get these geometric answers here, as long as the way you obtain the answer is justifiable. Everything is fine. Okay, let's take a look at the function 1 over z. That's going to be the most complicated of the three functions that we have here until we hit Moebius transforms, of course, which combine all those guys. And the function f of z equals 1 over z, well, it takes a number z, which in polar notation is r e to the I theta, and it maps it to the number, the output number w, which is 1 over r e to the negative I theta, right? Because 1 over r e to the I theta is just that. Okay, so that means the modulus is replaced with its reciprocal, and that is essentially a reflection across the unit circle in a certain geometric way. And the number is after that also reflected across the real axis because we're changing from e to the I theta to e to the negative I theta. And so that means geometrically, if this is the unit circle and here's our number z equals r e to the I theta, well then first of all we've got the reflection that gets us to 1 over r e to the I theta, and then actually as we flip across the real axis we end up with 1 over r e to the negative I theta, which is what 1 over z is. Okay, so again, even though this is one function and we ultimately want to think of it as one function, we again visualize it in stages. Okay, well, moreover, because when z goes to 0, 1 over z goes to infinity, and because when z goes to infinity, 1 over z goes to 0, the function can be extended to a continuous map on the complex numbers with infinity added, and we would do that by saying that we map 0 to infinity and infinity to 0. That is something because ultimately it makes sense to visualize lines as circles with infinite radius. We want to think about what happens to places where these functions are undefined and what happens to the point at infinity. Okay, so what does this function do to circles and lines? Well, here's the theorem. The image of a circle or a straight line under the function f of z equals 1 over z is a circle or a straight line. And here's again where, of course, we have to interpret the mathematical language correctly. Circle or a straight line is the union of the two, and that's mapped to a circle or a straight line, which does not mean circles go to circles and lines go to lines. It could include that some circles go to lines and some lines go to circles. And that is indeed what happens. So let's prove this. Let's take the function and break it up into real and imaginary parts here. If u plus iv is f of x plus iy, well then u plus iv is 1 over 1 over x plus iy, and we can turn the denominator into a real number by expanding with the conjugate, and we end up with x minus iy over x squared plus y squared, which means that u is x over x squared plus y squared and v is negative y over x squared plus y squared. And because this function is its own inverse, we have that x plus iy is f of u plus iv, and that means x is u over u squared plus v squared, and y is negative v over u squared plus v squared. And yeah, that's just by interchanging u with x and v with y. And therefore, if we're taking the equation of a circle or a line in the xy plane, which is our domain, then that transforms as follows. Now notice, this really is the equation of a circle or a line because, well, this form, of course, should be familiar to you. Sometimes people cancel out the a, but that would be x squared plus y squared plus bx plus cy plus d. That's the equation of a circle. It could also be the equation of a line because in this equation we do not exclude that a could be 0, and of course with a being 0 this would be bx plus cy plus d equals 0, and that's the equation of a line. So this really is the equation of a circle or a line, and that's another reason why people often like to treat circles and lines at the same time, their equations really are just matching up very nicely. Okay, if I have that in the domain, well, I can replace x with this expression, y with the other expression, and I obtain a u squared over u squared plus v squared squared plus v squared over u squared plus v squared squared, that's just the x squared plus y squared, b u over u squared plus v squared is bx, c negative v over u squared plus v squared, that's cy plus d. Now we're out of room, let's copy what we had on the previous slide. And well, this is now, if we add this up, of course, u squared plus v squared, one of those cancels, so we end up with a over u squared plus v squared plus bu over u squared plus v squared plus cv over u squared plus v squared plus d equals 0. And that means that a plus bu minus cv plus du squared plus v squared is equal to 0. And that's the equation of a circle or a line, right? It's just that the coefficients have been moved around a little bit. So this means that f of z equals 1 over z is a function that maps circles or lines to circles or lines, but you can also see if a is equal to 0, then the input would have been a line, and that goes to a circle, and if d was equal to 0, then the input would have been a circle, and that goes to a line, assuming always that the other numbers are not 0. Okay, I'm feeling a little strange right now. Give me a minute to pause. We'll get right back to Moebius transforms. And we're back. Sorry, sometimes when I start talking a lot early in the morning, I get a little lightheaded, and then I just need a quick break. But that's a teachable moment. If you ever get kind of dizzy when you're doing mathematics, you take a quick break, you keep doing mathematics. Mathematics is too much fun to let mere physical problems detract us from it. Okay, let's take a look at an example for f of z equals 1 over z. And if we want to find, for example, the image of the vertical line x equals c with c greater 0 under the function f of z equals 1 over z, well, and if we then also want to find the images of the half planes x greater than c and x smaller than c, well, what do? We have that c is equal to x, and x was u over u squared plus v squared. Well, that means that cu squared minus u plus cv squared has to be equal to 0 if we just bring the denominator over and then also subtract the u over to the left side. If we complete the square, well, we realize we have to take out the c, so we get a negative u over c. The term that completes the square is 1 over 4c squared, and c times 1 over 4c squared would be the 1 over 4c on the right side here. So that gives us c times u minus 1 over c quantity squared plus c v squared equals 1 over 4c. If we divide by c, we get u minus 1 over 2c quantity squared plus v squared equals 1 over 4c squared. And that image, therefore, of x equals c is the circle of radius 1 over 2c, the radius of the right side, which is centered at 1 over 2c and 0 in the y direction. Okay, so now the half plane x smaller than c, that contains the value z equals 0, and z equals 0 is mapped to infinity by 1 over c, and so that means the half plane x smaller than z is mapped to the outside of the circle, and that means the half plane x greater than c is mapped to the inside. Okay, we can also take a look at the image of the horizontal line y equals c with c not equal 0. Here's where we then have to be a bit careful to make sure we handle the signs right. And we also want to find the images of the half planes x greater than c and y greater than c and y smaller than c. And well, again, it's just c equals y, which is negative v over u squared plus v squared. Same computation as before. We bring everything to the left, we complete the square, and ultimately end up with the fact that the image of the circle of the line y equals c is a circle of radius 1 over 2c absolute value this time, right? Because we don't know if c is greater than 0 or smaller than 0. And it's centered at 0, 1 over 2c, coming straight from the equation of the circle. For c greater than 0, we have that the half plane y smaller than c goes to the outside of the circle, because when c is greater than 0, then this half plane contains 0, which goes to infinity, which is on the outside. And the half plane y greater than c goes to the inside because infinity goes to 0, and infinity is in y greater. Well, infinity is a bad example. You would have to choose something that is significantly bigger than c but not infinite, and you can find that that point goes to the inside. So that is something I would recommend to reason it out carefully one more time. I've tried to verbalize it here, but basically the idea is you just need to find out where 0 and infinity are and where they go and where they are going. For c smaller than 0, the half plane y greater than c goes to the outside of the circle, and that's because when c is smaller than 0, then 0 is in y greater than c, and that means that the half plane y smaller than c goes to the inside. So I guess we can just get away with figuring out where 0 goes. Sometimes you also have to consider infinity for half planes. That doesn't work too well because for half planes, of course, infinity can be considered to be in both of them. Okay, now let's take a look at the main topic of this presentation, which are these Moebius transforms. So let's see. When you've got 4 numbers, a, b, c, d, they're all complex, and we want them to satisfy ad minus bc not equal 0, then the function f of z equals az plus b over cz plus d. That's called a Moebius transform, or a fractional linear transformation. Basically, az plus b would be called a linear transformation, and then there is a fraction involved, so they call it a fractional linear transformation, or a bilinear transform, and we're going to motivate that name in just a little bit, I think. So note, yeah, the last name, the bilinear transform, is because we can rewrite w equals az plus b over cz plus d with ad minus bc not equal 0 as azw plus bz plus cw plus d equals 0, where ad minus bc is not equal 0, and there's a colon here. We're actually going to show that. But basically then this is something that is linear in z, it's linear in w, but it's not linear in both. So it's something that people then often call bilinear. Okay, how would that go? Well, you take your w equals az plus b over cz plus d, and you get rid of the denominator. You get wcz plus d equals az plus b. Multiply out the parentheses and bring everything over, and you end up with wcz minus az plus dw minus b, and that's exactly the forms that we have there, except that we also have to verify, of course, now that our a, which is c, times d, which is negative b, minus b, which is negative a, times c, which is d, that this is not equal to 0, but this expression is equal to ad minus bc. Just puzzle out the negative signs, and that was not equal to 0. Okay, another note, and that is that we're insisting here that this ad minus bc is not equal to 0, and we're insisting on that because otherwise at least one of a and d and at least one of b and c is equal to 0, and that means that the function will be pathological. It will be undefined or constant, and that's because, well, it's undefined in case c equals d equals 0, and it's constant in case a equals c equals 0, or a equals b equals 0, or b equals d equals 0. In every one of these cases, let's see, a equals c would give us b over d, that's constant. A equals b equals 0 would give us 0. B equals d equals 0 gives us az over cz, which is a over c, so it is constant in all of those cases. Or the other thing that could happen is if none of a, d, b, and c are 0, then we must have that by just solving for a, that a is equal to bc over d, but that would lead to f of z being az plus b over cz plus d. That would be bc over d times z plus b over cz plus d. Now we can factor a b over d out of the numerator, and if we do that, the numerator becomes cz plus d. That's because if you factor a b over d out of b, you end up just with a d, right? And cz plus d over cz plus d is 1, so this is b over d, which is constant. So in all cases, if ad minus bc is equal to 0, then f is undefined or constant. And we'll see later that when it's not equal to 0, then f is actually invertible. So in particular, it will not be constant in that case. So basically, this situation here this demand here takes out a few pathological cases, a few cases that are not as pretty as the rest. Okay, so now the theorem about Moebius transforms or fractional linear transforms is that any fractional linear transform f of z equals az plus b over cz plus d maps circles and lines to circles and lines. And the proof now comes straight from what we know about these first three maps that we have investigated. In case c is equal to 0, we have that f of z is a over d, z plus b over d, and that's, of course, mapping circles to circles and lines to lines because it's a composition of az and cz plus b. And in case c is not equal 0, we have that the function is this composition that we've talked about at the beginning, right? We first map z to cz, which is that we apply this function. We map cz to cz plus d, which means we apply this function. We map cz plus d to 1 over cz plus d, which means we apply this function. We map 1 over cz plus d to b minus dA over c, 1 over cz plus d, which means we apply this function. And we map that to b minus dA over c, cz plus d, which is what we had, plus a over c, which means we apply this function again. And if we now do the algebra with this, we find the common denominator. A over c becomes az plus dA over c divided by cz plus d. Puzzle it all out, and we end up with our fractional linear transformation. And all these functions in this decomposition map circles and lines to circles and lines, right? Because this is a composition, a decomposition of az plus b over cz plus d into a composition of functions of one of these three forms, and every one of these functions maps circles and lines to circles and lines. And so that means that these Moebius transforms also map circles and lines to circles and lines. That's the end of the proof. And notice that we did use AD minus BC not equal to 0 because we worked with this B minus DA over C, and that is non-zero only if AD minus BC is not equal to 0. Okay, well, now let's see, what else do we have? Right, we want to now establish that a fractional linear transform with AD minus BC not equal to 0 can be extended to a bijective continuous function from the complex numbers with infinity to the complex numbers with infinity. So this is going to be a one-to-one and onto function. And let's see, how do we do this? We're going to show that this thing has an inverse, right? So the formula for f maps c without the one place where it's not defined, namely negative d over c, that's where the denominator is not defined, to the complex numbers without a over c, which is the limit as z goes to infinity, and it can be shown that that value is not assumed. And if c is equal to 0, we just don't take anything away from the complex numbers. So regarding bijectivity, we can now note that the inverse is f inverse of w being negative dw plus b over cw minus a, and I deliberately left that out. What you can do to show that this is right is you either compute the inverse pre-calculus style, you set w equal to this right side and solve for w, or you could also prove it with a direct computation by just plugging f inverse into f and f into f inverse and show that either way you just end up with the identity function, so that either one of those compositions simplifies down to z. Because negative d negative a minus bc is not equal to 0, and that would be just basically this one times this one minus this one times this one, just as up here, we have that the inverse is also a Moebius transform. And the formula for f inverse now maps c without a over c to c without negative d over c, and you can see that just maps the original range to the original domain, which is what an inverse is supposed to do. And so for the extension to c union infinity, because the limit as z goes to infinity, az plus b over cz plus d equals a over c, and because the limit as z goes to negative d over c of this thing is infinity, we define f of infinity to be a over c and f of negative d over c to be infinity. That makes the function continuous on c union infinity. It's already bijective on these domains and ranges where there's one point removed. And so f inverse can be extended similarly to a continuous inverse for f on that thing. and that means that these Moebius transforms really map C union infinity bijectively to C union infinity as long as we have that AD minus BC is not equal to 0. Okay, what else can we do? Well, we want to show that these Moebius transforms are closed under compositions. So we want to show that the composition of two of these guys is again a fractional linear transform. Alright, well, first of all, we just have to bite the bullet and explicitly work with the composition. So f composed with g is f of pz plus q over rz plus s. We just substitute that in, right? This is a times whatever is inside plus b over c times whatever is inside plus d, and whatever is inside is just this complicated expression. Find the common denominator, right? apz plus aq and then plus brz plus bs divided by cpz plus cq plus drz plus ds. And now we realize that these two denominators here, of course, as soon as you go to the reciprocal of the denominator, cancel. So we end up with apz plus aq plus brz plus bs over cpz plus cq plus drz plus ds. And if we just sort that out, that's ap plus br times z plus aq plus bs. This is one number. This is one number. It looks complicated, but really is just one number because all these things are constant, divided by cp plus dr, which is one number, plus cq plus ds, which is also one number. And we can just set that equal to az plus b over cz plus d. And that means the composition has the right form. And it would be tempting to say, now we're done, but we still need to verify, because a Moebius transform always has, as part of its definition, that AD minus BC is not equal to 0. We still need to verify that. Now, considering what these things look like, that doesn't look like a lot of fun at all. So we could either do the computation directly, or we could somehow reason it out. You know what? Let's just try and reason that out, because the computation is epic. Both f and g, because they're Moebius transforms, can be extended to bijective functions on C union infinity. But that means that the composition can do the same thing, right? Because if g is extended to a bijective function on C union infinity, and it's composed with f, which can also be extended, well, then I just appropriately extend g and f, and I get an extension of the composition. So that works out perfectly. We have seen earlier also that if AD minus BC was equal to 0, then the composition would be undefined or constant, and in either of those cases the composition could not be extended to a bijective function on C union infinity. And that means AD minus BC must not be equal to 0. And that means we're done without any further computation, and that is certainly something to rejoice about. So, I mean, independent of how much or how little we may like these abstract arguments, this abstraction has been born out of need, the need being, of course, first of all, to have a guarantee that certain theorems always work, but we can see here also that sometimes the need comes simply out of a lack of motivation to do an epic computation, and it is very interesting throughout mathematics. I mean, very often either one or the other works and the other one does not, but there are sometimes nice situations like this one where one approach really significantly shortcuts the other one. And of course the art form then is to decide which one to use. Okay, let's take 3 distinct points, and that means they're complex numbers or infinity, and let W1 through W3 be another 3 distinct points, and I claim that then there is exactly one fractional linear transformation, exactly one Moebius transform, that satisfies f of z1 equals w1, f of z2 equals w2, and f of z3 equals w3. So that means that a Moebius transform is uniquely identified by what it does to 3 distinct points. This is very similar to results that you may have seen in pre-calculus that say that a quadratic function, for example, is also determined on what it does to 3 distinct points. It's just that these things are not quadratic functions. Okay, proof. Well, let's take those 3 pairs, and this is one of those proofs where somebody has thought about this stuff for a long time and then came up with something that just works out really neat. look at this. You take those three pairs, Z1, W1, Z2, W2, and Z3, W3, and they satisfy that W minus W1, W2 minus W3 over W minus W3, W2 minus W1 is equal to Z minus Z1, Z2 minus Z3, Z minus Z3, Z2 minus Z1. Okay, well, okay, like I said, somebody thought of this for a long time and has figured out how to do this. Let's at least verify that it is right. If we plug in Z1, W1 on the left side, we get 0 because of this. On the right side, we get 0 because of this term here. Great, okay, so that means Z1, W1 satisfies the equation because we get 0 equals 0. Z3, W3 satisfies the equation in an extended sense because if I plug W3 in here, I get 0 in the denominator. If I get Z3 in here, I get 0 in the denominator here. And so basically I would get in this extension of the complex numbers, I would really get infinity equals infinity, and that is considered satisfying the equation. If you don't like that, you could always just go ahead and multiply the denominators over, and you would get 0 equals 0 on both sides. So the equation is satisfied. And if we plug in the second one, well, I get W2 minus W1 times W2 minus W3, which is the same as W2 minus W1 over W2 minus W3. So I get 1 on the left. And if I plug the number Z2 in here, I get Z2 minus Z1 times Z2 minus Z3, which divided by Z2 minus Z1, Z2 minus Z3, which is 1 here also. So these 3 points satisfy that equation. Now let's let the left-hand side be L of W. Let's let the right-hand side be R of W. Well then, notice also that, this thing now is a Moebius transform, right? So let's see, the A would be W2 minus W3. The D would be negative W3 times W2 minus W1. The B would be negative W1, W2 minus W3. And the C would be W2 minus W1, which is right here. Notice that that is equal to, let's see, we've got this term is in common, this term is in common, so we just end up with negative W1 minus W3, so we get W1 minus W3 times the two other terms that were in common, and that's not equal to 0 because W1 through W3 were distinct, 3 distinct points. And so that means that L is a Moebius transform, and the same argument with Z's, W's replaced with Z's, show that R is a Moebius transform also. But that means if we apply the inverse transform on the left side to the displayed equation, we get the equation that W is L inverse composed with R of Z, which is a Moebius transform that is satisfied by Z1, W1, Z2, W2, and Z3, W3. And so that means there is a Moebius transform as required, and that is the other thing that the theorem says, right? It says there is exactly one. Yeah, I emphasized the exactly, but the equally important part in this theorem is that there is one to begin with. So it's determined by 3 points, but also any 3 points will give you a Moebius transform. Okay, so that's where we were at. And so now, in order to get the uniqueness, let's suppose for a contradiction that there are 2 distinct Moebius transforms f and g, so that f of zj equals wj equals g of zj for j equals 1, 2, and 3. Well, then zj is g inverse composed with f of zj for j equals 1, 2, 3. Sure, you just apply f inverse to this equation. And, well, g inverse composed with f, of course, is a Moebius transform, so I could call this thing az plus b over cz plus d. So that would mean for j equals 1, 2, and 3, we have zj equals azj plus b over czj plus d. And if I multiply that over, I get czj squared plus dzj minus azj if I bring that over. And the plus b should be a minus b. And yeah, now it is a minus b, and that's supposed to be equal to 0 on the right side. But notice that quadratic equations have at most 2 solutions, and this equation is supposed to be satisfied for 3 distinct points. If we want to be really really careful about that, one of the zj's could have been infinity, but if that had been the case, we would have had infinity equals infinity, and that only works if c is equal to 0, because otherwise the right side would go to a over c. And if c is equal to 0, well, then this equation would only be satisfied for one solution, or we would still have two real solutions for j equals 1 and 2, let's say. Okay, so either way, we have proved the result. And give me just a second. Yeah, so just let's pop everything up by one line, and we now realize, therefore, that we have a contradiction either way. Okay, we're almost done. We're going to now look at some examples of Moebius transforms, and that goes under the heading of mapping the upper half plane to the unit circle, which is a good example of a Moebius transform. And here's the theorem. A fractional linear transformation maps the upper half plane y greater than 0 to the unit disk z absolute value smaller than 1. And that means then the real line y equals, and in particular the real line y equals 0 to the unit circle z absolute value equals 1, if and only if it's of the form f of z equals e to the I alpha z minus z0 over z minus z0 bar, where the imaginary part of z0 is greater than 0. Let's prove that. Well, let's take a Moebius transform that maps a real line to the unit circle. Well, because that function doesn't map infinity to itself, we must have that c is not equal to 0. If c was equal to 0, this would be a linear transformation which maps infinity to infinity. And so we can assume without loss of generality that c is equal to 1. Otherwise, we could always just factor out a c in the denominator and stick that as a fraction into the numerator. And because f of infinity must have modulus 1, we also have that a is equal to f of infinity now, and that's because if c is equal to 1, then infinity will go to a. And that's because it has modulus 1, we can set that equal to e to the I alpha. And b over d absolute value, that's f of z absolute f of 0 absolute value. Well, because we plug in zeros here. And that's equal to 1, right, because the real line goes to the unit circle. And that means that b absolute value is d absolute value. So that means that f of z is actually e to the I alpha c, e to the I alpha z plus b over z plus d, which is equal to e to the I alpha z plus b e to the negative I alpha over z plus d. We just factored out the e to the I alpha to get the right form here. And that's e to the I alpha z minus z0 over z minus z1. So we fought really hard to get all sorts of things there, but in the end we just say that this is z0 and this is z1, with the added caveat, however, that b absolute value is equal to d absolute value. So that means because this thing here has absolute value 1, we have that z0 absolute value is z1 absolute value, which is not equal to 0. And that now means that 1 is equal to f of 1, which is tossing out everything that has absolute value 1. That's the absolute value of 1 minus z0 over 1 minus z1, which is 1 minus z1 absolute value equals 1 minus z0 absolute value. And those absolute values, of course, if I square that, I can work it out. 1 minus z1 times 1 minus z1 bar equals 1 minus z0 times 1 minus z0 bar. And if I multiply that out, I get 1 minus z1 bar plus z1 bar, 1 minus z0 bar plus z0 bar. Remember that z0 and z1 have the same absolute value, so these last terms are both equal to 1. So that means after we also toss out the negative signs, we end up with z1 plus z1 bar is equal to z0 plus z0 bar. And that means that the real parts must be equal, because after all, this just gives us twice the real part on either side, and then we just cancel the 2's. And because they have the same absolute value, well, if two complex numbers have the same absolute value and the same real parts, then the squares of the imaginary parts must be equal to each other, which means the imaginary parts must be either equal or negatives of each other, and that means we either have that z1 is equal to z0 or z1 is equal to z0 bar. And f is not constant, which means that z1 cannot be equal to z0, which means that z1 must be equal to z0 bar. And that means that f of z is e to the I alpha z minus z0 over z minus z0 bar. And for y greater than 0, we must have that the image of f of x plus iy for any x has absolute value smaller than 1. And that means that x minus real part of z0 plus y minus imaginary part of z0, both squared, that's the square of the numerator, that must be smaller than x minus real part of z0 squared plus y plus imaginary part of z0 quantity squared, which is the square of the absolute value of the denominator. And the only way that can happen is if the imaginary part is greater than 0, because we have y greater than 0, and if the imaginary part was smaller than 0, then this thing would be greater than y, this thing would be smaller than y, everything else cancels, so that inequality couldn't be justified otherwise. Okay, conversely, if f is of this form with imaginary part greater than 0, well then for all real numbers x, we have f of x is just obtained by plugging into the formula, but that's e to the I alpha x minus z0 over x minus z0 bar, and the absolute value of a number is equal to the absolute value of its conjugate, which means that f maps anything on the real axis, anything that is of the form x plus 0 times I, to stuff that has absolute value equals 1. And moreover, f of I, which is on the units in the upper half plane, well, that's e to the I alpha I minus z0 over I minus z0 bar. Well, that's e to the I alpha negative real part of z0 plus I times 1 minus imaginary part of z0 divided by negative real part of z0 plus I times 1 plus imaginary part of z0. That has a modulus smaller than 1, again, because imaginary part of z0 is greater than 0. So that means that if I take the square of the absolute value up here, then that is smaller than the square of the absolute value down here, and that means that the modulus is smaller than 1. Okay, so f maps therefore the upper half plane to the unit disk. And that's what we wanted to prove. Okay, we're going to finish out with some concrete examples, I think, where we're actually going to apply this theorem. Take a look at the fractional linear transformation w equals f of z equals z minus 1 over z plus 1. I claim that maps the right half plane, y greater than 0, to the half plane, to the right half plane, v greater than 0, and it maps the half plane x greater than 0. Whoops, it maps the upper half plane, the upper half plane, y greater than 0, to the upper half plane, v greater than 0, and it maps the half plane x greater than 0, the right half plane, to the unit disk. So this is just what we've had, only rotated a bit. And so for the first part, note that for any real number x, we have that f of x equals x minus 1 over x plus 1, which is also real. And that means it maps the real line to the real line. And f of I is I minus 1 over I plus 1. If we expand with 1 minus I over 1 minus I, we end up with, well, let's just multiply that out. The modulus of the denominator here is just number times its conjugate, so we just get the square of the modulus, and that's 2, that's correct. And we have that negative 1 minus another negative 1. If we multiply that out, that ends up giving us no real part, and 1 times I minus 1 times negative I gives us 2I. So this really is 2I over 2, which is I, and that is in the half plane v greater than 0, and so that means that y greater than 0 goes to v greater than 0. For the half plane and the unit disk, we now argue as follows. When x is greater than 0, well, note that f of z equals z minus 1 over z plus 1. If I multiply that with I in the numerator and in the denominator, I get iz minus I over iz minus negative I, and that is just the form that we had in the previous theorem, only that our variable is iz instead of I, right? So then we note that the function, when we map z to iz, that maps the right half plane to the upper half plane, and by the preceding theorem, the function that maps z to z minus I over z minus negative I, that maps the upper half plane to the unit disk z absolute value smaller than 1. And so that's it. That means we have taken this function, we have shown that when something is x greater than 0, then we first map it to IZ and then to this thing here, and that maps the right half plane to the unit disk. Okay, this should be the final example. As we do these transformations, of course, Moebius transforms are well understood and they are good, useful building blocks in these transforms. But then, of course, we also want to know how this interacts with other functions, for example, with the principal branch of the logarithm. So let's take a look at the transform principal branch of the logarithm of z minus 1 over z plus 1, and we claim that that maps the right half plane, the upper half plane, y greater than 0, onto the strip 0 smaller v smaller pi. Okay, let's think that through. By the preceding example, by the preceding example, we have that when we map z to z minus 1 over z plus 1, that maps the upper half plane y greater than 0 onto the half plane v greater than 0. The half plane v greater than 0 consists of numbers of the form r e to the I theta, where theta is between 0 and pi, and the principal branch of the logarithm maps these numbers to ln r plus I theta, and that is, it maps the half plane to the strip 0 smaller v smaller pi, and because ln r is always greater than 0, we don't map it to the whole strip, we just map it to the right half of that strip. So it really isn't a function that is onto. Give me a second here. Sorry, I misspoke. This presentation has been going on long enough, so let's finish it out. Of course, the logarithm is not just positive. The logarithm takes on any value between negative infinity and infinity for r going from 0 to infinity, which it does. And so that means that this really maps the half plane onto the whole strip 0 smaller v smaller pi. Alright, well, it has just been proved that I do need a break. You may need a break too, but either way, take a look at some homework problems, work with these transformations, learn how to visualize how planes go to other planes, how planes go to disks, how lines go to circles, circles go to lines, and so on. This stuff actually, even though it is certainly demanding because we are connecting algebra with geometry, once you see the pictures in your mind, it is quite beautiful, and it's quite satisfying to actually realize that, hey, I can see these pictures in my mind. So have fun with them, and I'll see you in the next presentation. Function up into a composition of simpler functions, because take a look at this. Like I say, as such, they seem hard to analyze, but this function, f of z equals az plus b over cz plus d, can be represented as a composition of simpler functions. So I could take my z and I could map it to cz, and that would be just applying the function f of z equals number times z, and you can see up here in our table of contents that we will investigate various simpler functions separately. So yeah, I could go from z to cz, from z to cz, by just multiplying by a number. I can go from there to cz plus d by just adding a number. I can go from there to 1 over cz plus d by taking this result and plugging it into the function 1 over z, into the function that multiplies everything to its reciprocal. I can go from there to this expression, and even though this looks complicated, I'm just multiplying with a number. So this is another application of this function here. And I can go from there to this expression. Well, all I've done here is I've taken this term out front, put it in the numerator, and then added another. Pay special attention to what these functions do to circles and straight lines, and that is because ultimately it turns out that Moebius transforms map circles and straight lines to circles and straight lines. They might map circles to lines, some circles to lines, and some lines to circles, but overall the union of these geometric objects will be mapped to itself. And if we're thinking of the complex plane, then that does make a bit of sense, because a straight line could always be interpreted as a circle with infinite radius. That feels a little strange, but it is actually something that is quite sensible to do here. Okay, so let's take a look at the function f of z equals z plus b. Well, that function takes a region and shifts it by b, right? That's all it does. So if we have a point B, a point is of course always to be identified with its position vector. And if we then have a region R here, well then all we do is we attach this position vector and shift the whole region by that vector to get terms. So I've only applied this function one more time. And then we do a little bit of algebra with that. We find the common denominator, and as we find the common denominator, well, a over c times cz is az, and a over c times d is dA over c. And you can see now that the dA over c's cancel, and we actually end up with az plus b over cz plus d. Especially in this part of the course, this approach of taking a function and breaking it down into a composition of functions that we have a chance to analyze is very, very common. And so as we go through this, you will develop quite an eye for these kinds of decompositions. Okay, so what that means for the task at hand, for the first task at hand, which is ultimately to analyze Moebius transforms, is we must investigate what the functions f of z equals z plus b, f of z equals az, and f of z equals 1 over z, what these functions do to an input region. And we will here pay with this second dimension, this extra dimension of the complex numbers, we can do a little bit more on the geometric side. In this first presentation, and we're going to talk about these deformations a little bit longer than just one transformation, we will ultimately investigate the so-called Moebius transforms, and yeah, they really are named after a gentleman named Moebius, and I would presume that he was the one who, for the first time, really investigated these transforms. They're also called fractional linear transforms, and basically they are of the form f of z equals az plus b over cz plus d. And you can rightly say that, well, those functions actually are already quite complicated, and indeed it would be, at least for me, not possible to really track the cumulative geometric effect of a transformation like that just from that formula. But here is where we're also going to very much train our ability to break a function. Okay, no more residues, at least for a while. We're going to now talk about Moebius transforms, which are named after the German mathematician Moebius, whose main contribution to mathematics was to invent Moebius transforms. And that is what counts for humor in an advanced math class. Let's take a look at what Moebius transforms do. The main idea is that we want to track what a function does to a region. So basically, given a region R, we want to determine the shape and position of the region f of R, where f is an analytic function. That is a very good visual exercise. It allows you to really determine how a shape is being deformed by a transformation. It trains the ability, therefore, to visualize flows, for example, for fluids. It reveals the geometric aspect of functions that is not really present for functions on the real line, and that's because the real line is one-dimensional. You take an interval, you stick it into a differentiable function, you get an interval back, and that's it. Here